We're looking at section 6.3, part 2. The main thing we're going to be trying to do here is do some graphing as well as finding inverses for exponentials and logs. I want to review just a few logarithm rules though before we go on. I just want you to simplify this. If I gave you log base 6 of 36, what would that answer be? What you have to think of is 6 to the what is 36, and that's going to be 2, so you should have gotten 2. What if I give you log base 4 of, let's say, 1 over 64? Do you know what that is? If you don't, you know you could use a calculator, but hopefully you can think of it this way. This means 4 to what power would give you 1 over 64. Well, you should know 4 times 4 is 16 times another 4 is 64. So it would be 3, 4 to the third, but to get it to go to the bottom, it would have to be negative 3. So hopefully you remember that kind of thing. All right, now on to finding inverses. To find an inverse, we switch x to y, y to x, and we solve for the new y. So solving this, I'm going to switch y to x, x to y. Now to solve for this, I'm going to have to rewrite it in a logarithm because I want to be able to solve for y. So I'm going to switch these sides. We're allowed to do that. And now I'm going to write it as log, find the base, swirl it around, equals y. So log base 6 of y, or of x rather, is what y is equal to. And these two are inverses. I'd like you to look at what inverses are on the calculator. So if I graph 6 to the x, and now I'm going to graph this one. I go under math and I do log base 6 of x. All right, now look at this. Here's my first function. It's exponential growth. Here's my next one. It's a log function. And it actually keeps continuing down like this. Can you see how they are inverses? Anytime it's a reflection over the line, y equals x, that means that they're going to be inverses of each other. And this one would be. Remember, this keeps going down. The calculator doesn't show it, but it does. All right, let's find the inverse on the next one. So y becomes x, and x becomes y. To solve this for y, though, I'm going to have to rewrite it as an exponent. So I'm going to have find the base, come across, back around, and so that's going to be the inverse function. Let's try the next one. Here's our y becomes x becomes y. Find the base. What is the base? E, right? So I'm going to have e to the x equals y plus 3. Solving for y now, though, I'm going to have y equals e to the x, and then that's going to be minus 3. And that would be the inverse. On this one, here's our original. Y becomes x, x becomes y. Rewrite it as a log. So it's going to be log, find the base, come around, equals 6y. Now instead of writing log base e, I should write it as just natural log. So it's just going to be natural log x. Then I don't have to put the base because I know the base. Equals 6y, divide by 6, and so this would be the inverse. So these two are inverses of one another. All right, parent graphs for logarithmic functions. The graph of f of x equals log base b of x is shown below for b greater than 1 and for b in between 0 and 1. Because f of x equals log base b of x and g of x equals b to the x are inverse functions, the graph of f of x equals log base b of x is the reflection of the graph of g of x equals b to the x in the line y equals x. That's what I was talking about up here. If they're inverses, it's going to be a reflection in the line y equals x. So right here, we're looking at y equals b to the x and y equals log base b of x. They're inverses. This one has key points of 0, 1, and 1 base. This one has key points of 1, 0. See how x became y became x? And what do you think the other key point is on this one? Base 1, right. So this is the way these are going to look if our b is greater than 1. Now we can also have a b value that's in between 0 and 1. So if that base is like a half, a fourth, a third, a fifth, whatever, anything in between 0 and 1, here's the way b to the x looks like. Like y equals 1/2 to the x, for example. That's going to be a decay function. The inverse of that decay function is going to look like this. We still have the key points, 0, 1, 1 base. It's just that now that base is going to be a fraction, so it's going to be a value that's in between 0 and 1, so it's going to be lower than this one. That causes it to be decay. Okay? All right, so we're going to do some graphing here in a minute. Notice that the y-axis is a vertical asymptote of the graph of f of x equals log base b of x. The domain of f of x equals log base b of x is x greater than 0, and the range is all real numbers. Our key points for logs are going to be 1, 0, and base 1. Remember for exponentials, it was 0, 1, and 1 base. This is an inverse, so x and y switched. Remember how the domain of the other exponentials was all real numbers? Well, now the domain for logs is all real numbers. Everything switches. All right, graph the function, determine the asymptote of the function, find domain and range. We're going to use key points. Our key points for logs are always going to be 1, 0, and base 1. But then we're going to have to apply transformations. So we're going to see if we have any. What's this going to do? If x gets replaced with x plus 1, what's the shift? Left 1. So these points are going to have to go to the left 1. So graphing this, I've got the point 0, 0. I've got the point 1, 1. Now, normally our vertical asymptote up here for this log right here, it was x equals 0. And even for this log right here, that vertical asymptote was x equals 0. That's what it should be. But we had a shift to the left 1. So it was x equals 0, but it got shifted to the left 1. So now it's going to be like that. And so now the asymptote then is going to be x equals -1 because it got shifted to the left 1. Here's the way this is going to look. It keeps going up just very slowly. The domain is going to be from -1 to infinity, and the range is going to be -infinity to infinity. When you're doing these on the big ideas, I don't want you using a calculator, but I want you to see how you can check it. I can just go under math, and I can go down to log base, and I can put in log base 2 of x plus 1. I'm going to do a zoom 6. Here's the way it looks. It does keep going down. If you don't make it go down on the quiz or test, I'll have to take points off, because that means you're just looking at the calculator, not understanding that it keeps getting closer and closer to that asymptote. If I want to check my table of values, I should see my point 0, 0, and 1, 1, and I do. All right, let's try this one now, making our chart. So normally our key points are going to be 1, 0, base 1. But what's this -4 going to do? It's not in with the x, it's separate. So it's going to take this down 4. So let's plot the points. We've got 1, negative 4, and we've got 1/2, negative 3. Our vertical asymptote is supposed to be x equals 0. If we shift that down 4, it's not going to change it any. That asymptote is still going to be x equals 0. When that b value is in between 0 and 1, this is the way that log function looks. So I know that this is going to look like this. There's a graph of it. The asymptote is x equals 0. The domain is going to be 0 to infinity. And the range is going to be negative infinity to infinity. And these would be the key points that I would ask you for. All right? That's all there is for that. Remember these key points. The key points for these logs, 1, 0, base 1. This is for logs. For exponents, those key points, do you remember them? 0, 1, 1 base. So that's if we have exponential, but we don't have exponential here. We've got logs on both of these. Okay?